Okay, so hello and welcome back. So the next question that we have here is question number 10, which is basically find the number of all onto functions. Find the number of all onto functions from the set basically 1, 2, 3 and so on and so forth all the way up to n to itself. Okay, now basically a function, as you know, is basically if you have a set, for example, suppose that you have a set over here. This is some set A, for example, and this is some set B, and suppose that you have some elements over here and some elements over here. Now a function is basically, well, you could argue that, for example, this is a relation, for example, from A to B, right? So you could do whatever that you want. So for example, you could call this a relation. This is a relation R, for example, from A to B. So there is no rules over here. Whatever sort of relation that you want to define, you can define, and it doesn't have to be anything. I mean, you don't have to follow any rules as long as the relation is basically a subset of the Cartesian product of A and B, then basically the relation is a relation. This is not the best way that I could have said it, but hopefully you get the idea. Is a relation, meaning that basically you have some set A, for example, meaning that you have some set A over here, some set A, you have 4 elements over here, and you have some set B over here, and you have, for example, 4 elements over here. Now the Cartesian product of A and B is basically, for example, let's call this 1, 2, 3 and 4, and A, B, C and D, and then the Cartesian product of A and B is basically, for example, as you know, 1 with A, 1 with B, 1 with C, 1 with D. Then you have 2 with A, 2 with B, 2 with C, 2 with D. Then you have, for example, 3 with A, 3 with B, 3 with C, 3 with D, and then you have basically 4 with A, 4 with B, 4 with C, and 4 with D. So you get basically 4 times 4, which is equal to 16 ordered pairs here, meaning that you get basically all of these ordered pairs, 1 comma A, and then you get 1 comma B, for example, and then you get 1 comma C, you get 1 comma D, and so on and so forth, all the way up to 4 comma D, all the way up to 4 comma D, and the total number of these ordered pairs becomes 4 times 4, which is equal to 16 ordered pairs here, right? Now from these 16 ordered pairs, any meaning that if you take this as a set, now you can say that basically any subset at all, any subset of the set A Cartesian, the product of the Cartesian product of A and B is called a relation from A to B, right? Meaning that, for example, I could take, for example, I can take some relation R1 and call it, for example, 1 comma A and 1 comma B and 1 comma C, and call this a relation R1, just like that. I mean, it doesn't have to have any specific rules, or I don't have to abide by any sort of specific rules. This can be a relation. I can define a relation R2 as, for example, 1 comma A, right? And that is basically, these are all valid relations that I can define from A to B. Now, once we have basically the concept of relations, once we have understood the concept of relations, there is a specific type of relation which is called a function, right? So what that is that you can see that there is all kinds of mapping from, for example, 1 to A, 1 to B, 1 to C, 1 to D, and 2 to A, 2 to B, 2 to C, and 2 to D, and so on and so forth, all the way 4 to D over here. Now, in order for, and then you can pick a subset of this set of elements and then call it a relation. Now, in order for any of these relations to be a function, basically in order for any relation to be defined to be defined as a function, the condition is that every distinct element of the domain of the function, every distinct element of the domain of the function must have a distinct image in the codomain of the function. Right? So here I'm saying that every distinct element of the domain of the function, meaning that, and these are basically 1, 2, 3, and 4, each and every one of these needs to have a distinct image in the codomain of the function. And so what that means is that, let's say that I pick a subset of this, the Cartesian product of A and B, as follows. For example, I take my A as, for example, let's say that this is 1, for example, 2, 3, and 4. And I take, for example, 4 elements here. Let me redraw this. This was not. So let's take that I have 1, 2, 3, and 4. And I have A, B, C, and D over here. I have A, B, C, and D over here. And so over here, basically what we are saying is that basically every distinct element here, is supposed to have a distinct image in the codomain of the function. And And basically, this is the domain of the function, and this is the codomain of the function. That means that each and every one of these elements is supposed to be mapped to something in the codomain of the function. So this is your domain, and this is your codomain. Right? Now, that means that I have to map this to some element over here. For example, suppose that I map it to this one. This has to be mapped to something. I could map it to this one. This has to be mapped to something, and this has to be mapped to something. Now, so here basically what I'm saying is that every distinct element of the domain of the function must have a distinct image in the codomain of the function. If I call this, for example, f, now I can say that, for example, f of 1 is equal to a. I can say that f of 2 is equal to a. I can say that f of 3 is equal to b. And I can say that f of 4 is equal to c. And it doesn't really matter if d is not the image of anything under f. That doesn't simply matter, because the condition that we have is basically on these elements in the domain of the function, not on these elements in the codomain of the function. You could have 1,000 elements in the codomain of the function which are simply not the image of any element in the domain of the function, and f would still be defined as a valid function, right? So far we have basically we have defined the function successfully, and we have no problem. Now basically there are different types of functions, and depending on how you do this mapping, you could have different types of functions, meaning that one type of function that is very popular is a 1-1 function. Another type of, as opposed to the idea of a 1-1 function, you have a many-1 function. And and then you could have a 1-1 function, a many-1 function. There is another type of a function which is called an onto function, and there is another type of function which is called a bijective function. Right? So a 1-1 function is basically also called an injective function. A many-1 function doesn't have any such names as far as our text is concerned. An onto function is also called a surjective function. And a bijective function is also another type of function that we will talk about. So now what we have here is that, let's take a look at each of these types of functions. So basically a 1-1 function is the type of function. So first of all, if I have 1, 2, 3, and 4 here in the domain, and a, b, c, and d in the codomain, if I have these two sets over here, this is your domain, this is your codomain. A 1-1 function is the type of function in which basically, for example, 1 is mapped to A, 2 is mapped to B, 3 is mapped to C, 4 is mapped to D. This is a 1-1 function. But if I have the same two sets, and 1, 2, 3, and 4, and if I do the mapping this way, A, B, C, and D, and if I say that, if I do it this way, now you can see that basically f of 1 here is equal to A. Also f of 2 is equal to A. You can see that if I take 1 and 2 and x1 and x2, I can write f of x1 is equal to f of x2 is equal to A, and x1 is equal to 1, and x2 is equal to 2, which means that x1 is not equal to x2. That means that two distinct elements of the domain of the function have the same image in the codomain of the function, and so this type of function is actually called a many-one function. On the other hand, every distinct element in the domain of this function has a distinct range, has a distinct basically image in the codomain of the function, and so this type of function is called a many-one function. Moreover, you can see that this function there is this element d, which is not the image of any element in the domain of the function, and so this function is you cannot call it an onto function or a surjective function, but you can see that every basically member of the codomain of this function is actually the image of some element in the domain of the function. That means that there is no such element in the codomain of the function that is not the image of some element in the domain of the function. There is no element in this set that has been left alone. And that means that basically this function is called an onto function, but this function is not an onto function. Now you can see that this function is 1, 1, which means that it is injective, and it is onto, which means that it is surjective, and therefore you can say that this is a bijective function, meaning that a bijective function is the type of function which is injective and also surjective, right? So now the question that we were supposed to answer here is basically we wanted to find the number of all onto functions, which is basically this type of function where none of these elements in the codomain has been left alone, and all of these elements is the image of some element in the domain of the function, right? So you want to find that the number of all onto functions from this set to itself, which means that basically if you have this set over here 1, 2, 3 and so on and so forth all the way up to n, and suppose that this is the domain of your function, and you have the same set over here 1, 2, 3 all the way up to n, and this is your codomain of the function. Now, in order for the function to be onto, what that means that every element in the codomain of the function, which is the set of natural numbers, is basically the image of some element in the domain of the function. That means that every element here is mapped to some element here, and that means that basically no element here is left alone. Which means that to make this a little bit simpler, because this is an infinite set, this is an infinite set, to make this a little bit simpler, I'm going to start with a simpler case, meaning that let's say that I have a set over here, for example, 1, 2, 3, and 4, and I have A and the same set, basically, the same set 1, 2, 3, and 4, right? So 1, 2, 3, and 4, 1, 2, 3, and 4. Now, in order for this function to be onto, I have to, for example, do something like this, meaning that I have to map 1 to 1, 2 to 2, 3 to 3, 4 to 4. Or I could do it this way, meaning that I can say that, for example, you have 1, 2, 3, and 4, and you have 1, 2, 3, and 4, and then basically 1 is mapped to 2, 2 is mapped to 1, 3 is mapped to 4, and 4 is mapped to 3. This is also onto. So this function, if I call it f, this is onto. If I call this function, for example, g, this is also onto, because all of these elements are images of some element in the domain of the function. All of these elements are the images of some elements in the domain of the function. So now our goal here is to understand in how many ways can I actually do this, meaning that, for example, another way of doing the same thing would be to, for example, write this as you have 1, 2, 3, and 4, and you have 1, 2, 3, and 4 here, and then you can, for example, map 1 to 4, 2 to, for example, 3, 3 to 1, and 4 to 2. That's also another way of doing it. As long as every element here is covered, you have no problem, you're good to go, right? So what that means is that now I want to know in how many ways can I do this, meaning that in how many ways can I create an onto function, basically going from a set to itself, any set to itself. And any set, if you go to itself, you have the same number of elements in both of the two sets. That would be again that would be basically the same type of situation, meaning that you go from 4 elements to 4 elements. If your set has 5 elements, then you go from 5 elements to 5 elements. If your set has 6 elements, then you go from 6 elements to 6 elements, and so on and so forth. Which means that logically, if your set has n elements, 1, 2, 3, all the way up to n, you're going from n elements, you go from n elements to n elements, which is basically, again, the exact same type of situation. So let's see if we can figure out in how many ways we can actually do this sort of thing. Okay, so now as you can see, there are probably many different ways of basically relating these elements together. But one thing which is basically there are a few things that are important here. And what's important here is that, as you can see, in all of these different types of configurations, basically what happens is that suppose that I have these 4 elements here, right? Suppose that I have these 4 elements here, for example, 1, 2, 3, and 4, and I have 1, 2, 3, and 4. Now, what happens is that if I can take this one and map it to any of these elements over here, because all of these 4 elements are now free, and so I can map this one to 1, I can map it to 2, I can map it to 3, or I can map it to 4. Let's say that I map this 1 to 1. So what that means is that this 1 has been mapped to 1, and so basically, since my function is supposed to be onto, then that means that basically when I want to map 2 to some element, then I cannot map it to 1 anymore, because then 1 has been taken, and so 1 is not free anymore. Meaning that I have 3 choices available. I can map it to 2, I can map it to 3, I can map it to 4. So let's say that I map it to 2. So then, again, when it comes to 3, when I want to map it to something, I have 2 choices available, meaning that I can map it to 3, or I can map it to 4. And then when I have 4, I have only 1 choice available, which is only 4, right? But when I start, basically, in the beginning, I have 4 choices available. After I have made the first choice, then I have 3 choices available. Then once I have chosen 2 of them, then I have two choices available. When I have chosen 3 of them, then I have 1 choice available, right? Meaning that what that means is that repetition repetition is, I think repetition is supposed to be written this way. If I'm not mistaken, let me see. Repetition. Let me see. Repetition. Yeah. So what that means is that basically number one, repetition is not allowed. Is not allowed, right? So since repetition is not allowed, then I can, basically that's then how you can relate those elements together. And so that means that first you have to choose one of them, and then you can choose any other three of them, then you can choose any other two of them, and then you can choose the last one. And then again, the process basically, continues with the same type of process, meaning that I choose one of them, and then I can choose any other three of them, right? So then I choose the second one. Then I can choose any other two of them. So I can choose the third one. And then I can choose the fourth one, and so on and so forth. And I can do this in any order that I want, meaning that instead of, for example, choosing one first, I can choose four first, and then I can go for three, and then I can go for one, and then I can go for two. And I can do this in any way that I want, right? Now, this might remind you of something that we did in permutation, right? So in the concept of permutation, when we wanted to talk about the concept of permutation, what we said was that, for example, what is the total number of words that you can create using the letters of the word, for example, using the letters of the word rose. Repetition not allowed. Repetition not allowed. And the words created can be with or without meaning. Can be with or without meaning. Right? So we solved this problem in one of the chapters in class 11. And based on this problem, we laid the foundations of the concept of permutation, meaning that we said that so for example, now I want to use the letters of the word rose, R-O-S-E, in order to make 4-letter words. So I want to use R-O-S-E in order to make 4-letter words. 4-letter words. And these 4-letter words, how can I create these 4-letter words? So we said that in the beginning, well, over here I'm saying that basically repetition is not allowed. And also the words can be with or without meaning. It doesn't really matter whether the word that you create has meaning or not. That's not important here. So then I have a 4-letter word has basically four letters basically. You have 4 placeholders for the letters. So the first placeholder can, for this first placeholder, I have 4 choices to make, meaning that I can use an R over here, I can use an O over here, I can use an S over here, I can use an E over here, right? Now, suppose that I use R over here for the first letter. If I use R over here, that means that I have already chosen one of the letters, which means that and since repetition here is not allowed, then basically that letter cannot be chosen anymore. That means that one of the letters has been taken, and so now I have 3 letters to choose. So that means that for the second placeholder, I have 3 letters to choose. I can choose O, S, or E. O, S, or E. Now, so as you can see, now I have chosen 1 and 2 of the letters, and since repetition is not allowed, then I have 2 letters to choose. I have chosen R and O, so I can choose S and E here. Over here I have chosen R and S, so I can choose O and E here. And over here I have chosen R and E, so I can choose O and S here, right? Now, so we have chosen 1, 2, and 3 letters here. So this is the first letter, this is the second letter, and this is the third letter. So since we have chosen 3 letters already, then there is only 1 choice left, because, well, we had 4 choices and 3 of them have already been made, which means that basically only 1 letter is left. So R-O-S, so there remains only E. R-O-E, there remains only S. R-S-O, there remains only E. R-S-E, there remains only O. R-E-O, there remains only S. R-E-S, there remains only O, right? And so this is the first, this over here is the first placeholder, this over here is the second, the third, and the fourth placeholder. And so what that means is that now the word that I have created here is basically R-O-S-E. R-O-S-E. The word that I have created here is R-O-E-S. R-O-E-S. The word that I have created here is R-S-O-E. R-S-O-E. And the word that I have created here is R-S-E-O. R-S-E-O. The word that I have created here is R-E-O-S. R-E-O-S. And the word that I have created here is R-E-S-O. Right? So as you can see, this was basically the first letter. This was basically over here I have started with R, and starting with R, having these 4 letters, I have managed to create 1, 2, 3, 4, 5, 6 words here. 6 words here. That means that if I start with an O, then I will be able to create another 6 words here. If I start with an S, I will be able to create another 6 words here. If I start with an E, I will be able to create another 6 words here. That means that the total number of words that I can create here, the total number of words that I can create here would be equal to 6 plus 6 plus 6 plus 6, which is equal to 4 times 6, which is equal to 24 words. 24 words in total. Right? And we went through some calculation and some discussion once we were talking about the concept of permutation, and we came up with the formula n permutation R is equal to n factorial over n minus r factorial. And for example, in this example, you have 4 letters. You want to create 4-letter words. You want to create 4-letter words, and so based on this, you can say that your n is equal to 4. Based on this, you can say that your r is equal to 4. And so what that means is that then 4 permutation 4 is the same thing as 4 factorial over 4 minus 4 factorial, which is the same thing as 4 factorial over 0 factorial. 0 factorial is 1 is equal to 4 factorial. 4 factorial is the same thing as 1 times 2 times 3 times 4, which is equal to 24, which is basically the same number that we got over here, right? So what that means is that when you want to create basically then the total number of words that you can create using the letters of the word rows, repetition not allowed, meaning that when you choose a letter, then you're not supposed to choose it anymore. And the words that you create could have meaning, but the meaning is not important, with or without meaning, basically, is going to be equal to basically 4 permutation 4, which is actually equal to 4 factorial. Now what's interesting is that if you try the same thing for another 5 letters, for example, suppose that you have R, O, S, E, for example, L. Using these 5 letters, you want to create 5-letter words. You want to create 5-letter words. So based on what we said here, we can calculate that as 5 permutation 5, and that would be equal to basically 5 factorial over 5 minus 5 factorial, which gives you basically 5 factorial over 0 factorial, which is equal to 5 factorial. When you have 5 letters, and when you want to create 5-letter words, you will get 5 factorial. If you have 6 letters and if you want to create 6-letter words, you will get 6 factorial, 7 factorial, and so on and so forth, right? Which means that basically this number n factorial, you can denote this as n factorial. This number n factorial is actually the number, all the different number of permutations, which means that basically you can say that n factorial is the total number of permutations of n different objects. And when I say that the total number of permutations of n different objects, that means that you have, for example, I don't know, A, B, C, and D, and E. So you have 5 objects here. And you want to know the total number of all the different possible arrangements of these objects, meaning that you put your A first and B second, and then D, put a D after this, and then put your C in the end and E in the beginning, and so on and so forth. All the different such basically arrangements of these objects is going to be therefore, for example, 5 factorial. So then you can say that n factorial is the total number of permutations, or basically all the different possible arrangements of n different objects, basically taken all at a time, right? So as you can see, basically this concept of permutation is the exact same thing is the exact same concept that we can use over here. Meaning that, for example, meaning that in this particular example, we said that when you take 1, you cannot take it anymore. Once you have chosen 1, then you can choose either 2 or 3 or 4. Once you choose 1 and 2, then you cannot take those 2 anymore, and then you can choose either 3 or 4, and so on and so forth, right? So that means that then if you have basically 2 sets, or if you have basically 1 set, to be more exact, which means that if you have basically 1 set, that means that if you have any set and if you define a function, on a function which is of course an onto function on that set, basically the total number of basically onto functions, the total number of onto functions possible for that set, possible to be made using that set, would be basically, suppose that I take the number of elements of the set as, for example, of that set, for example, let's call the set A, for example. If I take n of A as the number of elements of set A, then the total number of, then you can say that the total number of basically onto functions definable on that set, definable on A, would be n of A whole factorial. Meaning that you simply have 4 objects over here, or basically these 4 objects would be n of A, the total number of the elements of that set. And then you are just simply calculating all the different permutations of those 4 objects, which is going to be basically n of A whole factorial. Or if you take, for example, the total number of the elements of this set as n, then that would be basically simply n factorial, right? Which means that basically you have all of these objects, and you are basically moving them around in every different way possible, and you want to know how many ways there are in order to basically put all of these 4 elements together in all the different possible ways. And that's basically the concept of permutation, which is nothing but, for example, which is nothing but basically n permutation r, which is equal to n factorial over n minus r factorial. Now, since in this situation n is equal to r, then you have n permutation. N is the same thing as n factorial, n minus n factorial, which is the same thing as n factorial over 0 factorial, which is equal to n factorial. Which means that if you have, for example, 4 objects, you would get 4 factorial. If you have 5 objects, you would get 5 factorial. Meaning that if you have 4 If your set has 4 elements, you'll have 4 factorial. If your set has 5 elements, you'll get 5 factorial. If your set has 6 elements, you'll get 6 factorial, and so on and so forth, right? So, which means that, now going back to the question, basically you can say that, based on this whole discussion, you can say that the number of all the onto functions from this set to itself would simply be n factorial, right? That's very simple and very elegant. This is basically one of the things that we had in miscellaneous examples, and I didn't understand it there, but then I had to think about it for a little bit in order to understand how basically the concept of permutation is applicable here, and then that's how it works. So I hope that you enjoyed this video, and we will continue the exercises in the next video. Thank you.